So last time we were doing, coming back to the point, we were doing something called the center of mass. The idea being that you have a system of particles, and the system of particles is a very nebulous kind of thing. It's up to you to define what do you mean by your system. Nothing physically changes when you redefine your system. It's just a matter of which particles you consider to be part of your system and which particles you don't. Okay, so if two billiard balls are colliding, you can consider all the atoms that are in billiard ball 1 as your system. You can consider all the atoms that are in billiard ball 2 as your system. You can consider all the atoms that are both in billiard ball 1 and billiard ball 2, okay, either one of the two, of course, as part of your system. So, and of course, nothing physically has changed. It's still the same two billiard balls that are colliding. Okay, so it's up to you how you define your system. Okay, defining different definition of the system of particles does not lead to different physics. Okay, it just leads to essentially the same physics is taking place. It just leads to a different description of what's going on. Okay, what we learned is that given a system of particles, first of all, you can classify the forces that are at play into two categories. You have external forces and you have internal forces. The external forces are the forces being exerted by all the particles outside your system of particles on the particles within your system of particles. So, for example, for two colliding billiard balls, if I consider my system as ball 1, all the forces being exerted by all the atoms in ball 2 on the atoms in ball 1, those are external forces. The forces being exerted by the billiard table on ball 1 are also external forces. The weight of ball 1 is also an external force because that's the force being exerted by the earth on the billiard ball. The earth is not part of your system the way that you have defined it. Okay? So you have something called the internal forces, which are the forces being exerted by the particles within your system on each other. So all the intermolecular forces, van der Waals forces, for example, between the atoms or molecules within the billiard ball 1, for example, if you have defined your billiard ball 1 as your system, are internal forces. And what we found out was something quite surprising, is that what we found out is that if you apply Newton's second law to each point particle within your system, and you put all these different equations that you get, one for the application of Newton's second law to each particle, and then you add them all up, you use Newton's third law, what you find is that it's really only the total external force that matters. The internal forces play some role, but overall it's really the external forces that are more important when it comes to the motion of your system of particles. When I say some role, well, when we go to energy conservation, it turns out that they do play some role, the internal forces, but the external forces are really what are dictating the overall motion of your system of particles. So the total external force can be written as we found out, as the total mass, the total external force equals the total mass of your system of particles times the double derivative of a position vector. As in, you can almost regard this, you can pretty much regard this as m times capital A, where capital A you can think of as kind of the average acceleration of your system of particles. Okay, and this capital R is known as your center of mass. The double time derivative of the center of mass, the double time derivative of this position vector times the total mass equals the total external force. Okay. And just to get started, last time I just showed you some simple examples of what this center of mass tells you. It essentially is the average position of your particles within your system, taking into account the masses of the particles. So particles with more mass are given more importance when it comes to capital R. So capital R, if you recall, is essentially the sum over all the particles of the position vectors, but you have to multiply each position vector with the corresponding mass of the particle, so that you give the particles with more mass more importance, and then of course you divide by the total mass. Okay. So the capital R is essentially the average position vector of your system of particles. And I showed you last time that if you just have 2-point particles, to begin with, if they have equal mass, you intuitively know that the center of mass should lie right in between the two particles, and that's exactly what we found out last time when we applied this definition of the center of mass. And then I showed you also that this definition also implies that the center of mass of 2-point particles lies along the line joining the 2-point particles. It's more shifted towards the particle with more mass. There are some other properties of the center of mass that you can deduce from this definition. So for example, if I give you 2 boxes and I say find out the center of mass of the 2 boxes, one way to do it would be, first of all, find out the center of mass of this box, find out the center of mass of this box. Then the combined center of mass of the 2 boxes can be found out by just forgetting about the 2 boxes, just considering these two points. This point has mass m1, this point corresponds to mass m2, as in you replace the 2 boxes by effectively 2-point particles of the first point particle having mass equal to the mass of the first box, the second point particle having mass equal to the mass of the second box. Then you forget about the boxes and just calculate the center of mass of these 2-point particles. Okay, and so on and so forth. Okay, in the readings I've kind of proven this, why you can do this. Okay, starting from this, but the proof is a bit long and boring. Okay, so I'm not doing it in class. Okay, but if you're curious, which who am I kidding, you aren't, you can always dig up the readings which I'll upload today. I haven't done it क्योंकि मुझे पता है अभी आप वर्क और एनर्जी भी कहीं बैठे होगे. Okay, but anyway, okay, so having done that, remember, you have to regard capital R as not something that is static. Capital R, generally the center of mass is generally also changing with time. If you throw something, if you launch your friend from the top of this building, your center of mass of your friend keeps on changing with time. Okay, so capital R in general is a dynamical quantity. The masses of all the atoms within your friend's body wouldn't be changing, but the position vectors of each atom within your friend's body would be changing. Okay, so these vectors are functions of time, and corresponding this capital R is function of time. And then we can ask all kinds of questions. Well, okay, how fast is the center of mass moving? How do you find that? How do you quantify how fast the center of mass is moving? क्या करोगे? Yeah, thank you. Okay. Calculate the rate of change of capital R will tell us, rate of change with respect to time will tell us how fast the center of mass is moving. That kind of gives you an idea of, on average, how fast the particles are moving. Because capital R is kind of the average position. And the derivative of capital R will correspond to something like the average velocity of this bunch of particles. Okay. Now, having gained some familiarity with the center of mass, one last example that I did remember was कि आपके पास एक पतली सी रॉड है और इसका center of mass कैसे निकालना है? Well, remember, capital R is the average position. Average क्या होता है? Average is always centered. भाई आप कहेंगे सर वो मुझे ग्रेड 8 से मुझे याद है, उसके बाद तो मैं स्टैट्स मैंने कभी की नहीं, so to speak. मुझे तो मीडियन होता था सर, दरमियान वाला. Well, median is something else. Median means that you order your data and you look at the darmiyan wala data point kaun sa, in the sense of your numbering. So if you have 11 data points, essentially looking for the 6th data point kaun sa. When I say that the mean, the average is the middle, it means that baki sare points are on average equally distributed. Okay, you look at the deviation of each point from the mean value, you add up all the deviations, you'll get 0. As I showed you last time. Okay, so किस point कहाँ अगर ये uniform rod है, कौन सा point है जिसकी mass equally distributed है? There's as much mass to the left as there is to the right. There's as much mass above as there is below. There's as much. That's why, intuitively speaking, we draw the center of mass. Okay, over here, आपने of course, red spot. एक जो है डंडा जो है यूं लटका देते थे, इधर एक हिंज होता था, एक डंडा बांध देते थे दीवार के साथ और फिर कहते थे टॉर्क वगैरह निकालो, मूवमेंट निकालो. सॉरी, रेड स्पॉट में ज्यादातर आई थिंक मोमेंट का लफ्ज प्रेफर करते थे जहां तक मुझे याद है, और फिर आप वेट इधर लगा देते थे, एक्टिंग एट द मिडल ऑफ द रॉड, और फिर वेट की वजह से टॉर्क आप कहते थे इस फोर्स मल्टीप्लाई बाय दिस लेंथ। याद आया? थैंक यू। देखिए रेड स्पॉट का सब कुछ याद है। ओके वेल, व्हाई इज द वेट एक्टिंग एट द मिडल ऑफ द रॉड? वेट तो एक्चुअली आपके रॉड के हर जो है वो छोटे छोटे पीस जो है, हर छोटा पीस जो है नीचे की तरफ अट्रैक्ट कर रही है। राइट, सो यू काइंड ऑफ हैव बीन यूजिंग दैट ऑल अलोंग। जब भी आपको कोई सिमेट्रिकल ऑब्जेक्ट हुआ है, आप इम्प्लिसिटली हमेशा उस सिमेट्रिकल ऑब्जेक्ट को एसेंशियली इन मेनी केसेस यू जस्ट रिप्लेस दैट ऑब्जेक्ट बाय अ सिंगल पॉइंट एट इट्स मिडल without even realizing it. You've been using this idea of the center of mass over and over and over again. Okay, and we'll come back to this when we do moments. Okay, but I just wanted to point out कि आप ये वाली चीज already देख चुके हो पहले high school में, when you were looking at these torques acting on rods and so on. You just looked at the force of gravity acting in the middle of the rod, because essentially that's as a point of symmetry. So if you want to find out the center of mass, the first thing that you always do is look for some symmetry. Try to figure out the point such that, as above, as below, as left, as right, as far, as ahead, as before, and so on. Okay. And then I just showed you last time that this also agrees with using the definition. So capital R equals the sum over all the point particles comprising this rod. And then you can say that, okay, this implies, because this is a thin rod, if I set up let me just do it slightly differently from what I did in class last time, मैं दरमियान में coordinate system set up कर देता। And I know that the center of mass should be at the origin now. This is a very thin rod, so never mind the y coordinate. I'm really only interested in the x coordinate of the center of mass. This equation implies that the x coordinate of this vector should be equal to 1 over capital M times Mi times xi, where xi are the x coordinates of all the point particles comprising the rod. Okay, as in the x component on the left hand side should equal the x component on the right hand side. So you have capital X equals Mi xi over capital M, and same for capital Y. The y coordinate of the center of mass should equal sum over I Mi yi over capital M, or in this case I'm just interested in the x coordinate. Now I have to do this sum, and this sum is over billions and billions and billions of particles. So to actually do this sum, I replace the sum by an integral. I essentially look at, instead of looking at this as sum over atoms, I essentially look at it as a sum over very, very small segments, very, very thin segments of the rod. So for example, let's look at this very thin segment. Yeah? Well, okay. Let me write it out. Capital R को मैं लिख सकता हूँ as and इसको मैं लिख सकता हूँ as sum over I Mi xi ex plus yi ey plus zi ez divided by capital M. और अब x components मैच करो. Capital X equals sum over I Mi xi over capital M. Capital Y equals Mi yi over capital M. जिस तरह ordinarily आप करते हो, given two vectors, if they are equal, their components should be equal. Okay. अच्छा. Okay, so I replace this by sum over these blue segments. This blue segment is not just only one segment, there are infinitely many of these blue segments because each segment is very, very thin. This blue segment is of thickness delta xi. I'm looking at the ith blue segment. This segment has essentially is located at x coordinate xi. तो इधर मैं लिख सकता हूं then xi, पहले मैं इसका mass जो है segment का बहुत छोटा है. So that I write as delta mi divided by capital M. Okay, delta mi is the mass of the ith segment. Essentially, I have chopped it up into small segments. the mass of each segment is very, very small. The x coordinate of each segment need not be small. जो इधर वाली segment है उसका x coordinate छोटा है? Of course not. उसका x coordinate तो L/2 है, where L is the length of this rod. Okay? And then I take the limit that I chop this up, I become the ultimate Kasai. Okay? So I chop it up into thinner and thinner and thinner segments such that delta mi approaches 0. If I delta mi approaches 0, this is from I is equal to 1 to n, where capital N now is not the number of atoms, it's the number of segments. If I chop it up into smaller and smaller segments, delta mi approaches 0, and what happens to capital N? Capital N approaches infinity. So ये क्या हो रहा है? This becomes an infinite sum in which each term approaches 0, but the number of terms also approaches infinity. तो क्या है ये? This is an integral. Exactly the same as you look at the area under the curve. When you look at the area under the curve, the area of each little thin rectangle, as you make the rectangle narrower and narrower, becomes smaller and smaller. But the number of those thin segments that comprise the area under the curve also blows up. So you get a longer and longer sum, but each term in the sum also becomes smaller and smaller. Okay, so then I can write down that capital X equals x dm over capital M, where of course this sum is over all the segments, as in, and where are the segments? Over the rod. So you just write down rod. Do this sum over the rod. Okay. Now you actually have to do this sum. To do this sum, जिस तरह आप कहते हैं सर, I give you an area, I give you a function, और कहूँ कि area under the curve निकालो from A to B. So you'll write this as f of x dx A to B. और फिर मैं कहूँ ओके इसको आगे सॉल्व करो. हाँ. Because essentially आपने ये वेक्टर निकालना है ना. You can find out the vector if you find out its components. जिस तरह मैं कहता हूँ कि पोजीशन वेक्टर निकालो किसी ऑब्जेक्ट का, you can say okay let's find out the x coordinate, let's find out the y coordinate. Once I have those, I have my vector. Okay. अच्छा ये अगर मैं कहूँ कि भाई एरिया अंडर कर्व निकालो, of course you look at me and say भाई सर f of x तो बताएं. To actually do this integral, you need to know the relationship between the heights of the rectangles, which is y in this case. ये कोई भी rectangle है उसकी height y है, and x. In the same thing, in order to do this integral, you need to have some relationship between x and the mass of each segment. x और dm के दरमियान कोई ना कोई relationship तो निकालनी है. So let's go back. और ये छोटा सा जो है इसकी length अब होगी dx, because you have made each segment very very thin. So इसका mass कितना है इस blue segment का? dm. So dm, the mass of this blue segment, equals the total mass of the rod, assuming that this is uniform, divided by the total length of the rod, multiplied by, you plug this in over here. Total mass of the rod divided by total length of the rod times dx. और अब आप integrate कर रहे हो over x. So when you integrate over the whole rod, कहाँ से कहाँ तक integrate करोगे? Well, the left end of the rod corresponds to x equals minus L/2. And this end of the rod corresponds to plus L/2, right? So this is equal to आपका आ गया minus L/2 plus L/2 x m over L dx divided by capital M. और ये बाकी तो अब आप भी कर सकते हो. m over L बाहर गया, 1 over m वैसे बाहर फिर minus L/2 x dx. ये इंटीग्रल किसके बराबर आएगा? आपका फेवरेट आंसर है 0. Why is this 0? x dx का एक एरिया अंडर कर्व ऑफ x फ्रॉम minus L/2 plus L/2 क्या होगा? इट्स अ स्ट्रेट लाइन. ये जो आपका फंक्शन आया है जिसको आप इंटीग्रेट करो वो स्ट्रेट लाइन है. ये L/2 है, ये minus L/2 है, तो ये टोटल एरिया क्या होगा? 0. Another way, let's do it explicitly. x square over 2 आ जाएगा, वो इंटीग्रेट करोगे, लिमिट्स डालोगे तो आपके पास क्या आ जाएगा? L square over 8 minus L square over 8. which gives you 0. Okay, this is another way of seeing this, that this is an odd integrand. Odd integrand का जब integrate करो from minus something to plus something, you will get 0. There's as much curve below the x-axis as there is above the x-axis. Okay, right. So surprise, center of mass किधर आया? इधर. Capital X आपका 0 आया, which means that the center of mass is at the origin. Okay, anyway, with that out of the way, okay, let's move on. Okay. अब आज के लेक्चर में you'll notice that this is quite different from many of the previous lectures. आज मैं बातें बहुत ज़्यादा करूँगा, equations बहुत कम लिखूँगा. So it's fun in that way, except कि वो equations लिखना जो है, that's quite tricky. Okay. You have to put a lot of thought before you write down the equations. Okay, so anyway. So now let's come to this. आप कहोगे sir, what is this good for? Okay. इस पर machine learning लगा सकते हैं. Okay. Probably. Okay. But anyway, before we go to that, पहले खुद तो कुछ सीख लो. Okay. Model को train भी तो करना है. Anyway, so you have this. What good is this for? And it doesn't look like much. Okay. Admittedly, it just looks like a more grown-up version of Newton's second law that you've already seen. But in practice, this is the most useful form of Newton's second law. Because in reality, remember, you're not dealing with point particles. In reality, you're dealing with objects. And objects are collections of point particles. So that's why in reality, this is the most useful form of Newton's second law, because this allows you directly to predict how an object moves from here to there. Okay. So the first thing it does, so this is useful for many things. This can literally send you to the moon. इंसान जो चांद गया था वो इसी की basis पे गया था. Essentially, this was the equation that was solved on a computer. और आप तो computer science के ज़्यादातर students हैं. Historically, for computer science, that equation is extremely important. क्योंकि इसी equation को solve करने के लिए there was a huge investment made back in the 1960s to make computers strong enough to actually solve that equation for many different cases. आपने रॉकेट बनाना है, रॉकेट के मोशन ने इस इक्वेशन को फॉलो करना है और इस इक्वेशन को आपने सॉल्व करना है फॉर एयर रेजिस्टेंस भी है और रॉकेट डिफरेंट चीजें कर रहे हैं एंड सो ऑन एंड सो फोर्थ. रॉकेट को फ्यूल इंजेक्ट कर रहा है, ब्ला ब्ला. विल डू सम ऑफ दैट in the next lecture. Okay, but of course हम सिंपल केसेस करेंगे कंप्यूटर के बगैर ही सॉल्व हो जाए. But you can write a very simple piece of code that actually solve this equation on a computer. Now, right now you can run that piece of code on something that is in your pocket, so you can run it while sitting in the washroom. But back in 1960s, you had to construct huge computers, a huge room, in order to solve that equation. Okay. Okay. Anyway, so the first thing I would like to highlight that what is this equation good for is that it allows you to go from. It essentially justifies your treatment, जो कि आप सारी उम्र करते आए हो. एक गाय को आपने क्लिफ से फेंका है, या आप अपने दोस्त को क्लिफ से फेंका है, या आपने एक बॉल को क्लिफ से फेंका है. तीनों क्वेश्चंस को आप एक ही तरीके से सॉल्व करते आए थे पूरी जिंदगी. This equation is precisely what justifies the use of the replacement of an actual object by a single point particle. So it justifies the replacement, objects replaced by point particles. When you are making this replacement, you are effectively saying, yeah, bhul jao us object ko. I am interested in just the motion of the center of mass of that object. The center of mass is effectively a point particle. वो एक single position है, single position vector है. That's it. If I know how the center of mass moves, I have some idea roughly of how that object is moving. Why I say roughly? क्योंकि of course object हो सकता है यूं घूम भी रहा है center of mass के गिर्द as it falls. So for example, as a very simple illustrative example, you have a box. आप उसको push करते हैं. कभी थोड़ा सा आपने ज़हन लड़ाया हो इस बात पे, जो कि of course आपने नहीं लड़ाया. You will always be wondering कि भाई ये इसको push कर रहे हो. Why do I always consider three forces acting on the box in the absence of friction? You just have to consider the weight acting on the box. You just have to consider the normal force acting on the box, and you just consider the force that the man force, yes, the force that the man is exerting on the box. और भी तो बेतहाशा forces हैं इधर. वो आपके atoms जो within the box are exerting, electrostatic forces on each other, electromagnetic forces on each other. वो इलेक्ट्रॉन आपने तो बोर मॉडल थोड़ा बहुत शायद देखा हो ए लेवल्स में, वो इलेक्ट्रॉन्स घूम रहे हैं. इफ यू अगर कोई चार्ज मूव कर रहा है तो कोई मैग्नेटिक फील्ड प्रोड्यूस कर रहा है बिकॉज ए मूविंग चार्ज को रिस्पॉन्स टू ए करंट, और फिर करंट्स जो हैं जो इसके एटम्स के अंदर हैं वो एक मैग्नेटिक फील्ड प्रोड्यूस कर रहे हैं, और बाकी एटम्स का चार्ज है तो वो मैग्नेटिक फील्ड क्यों नहीं, फोर्स क्यों नहीं? व्हाई डू यू कंसीडर दैट मैग्नेटिक फोर्स? Why don't you consider the electrostatic forces, the electric forces within the atom? I mean, or why don't you consider the intermolecular forces within the box? When I'm looking at the motion of the box, वो किधर गायब हो जाती है? There are so many other forces, but you never consider those. क्यों? You just, I mean, effectively as problem को आप कर लेते हो कि भाई एक नुकता है, उस पर ये force लग रही है, ये एक weight लग रहा है उसका, और एक नॉर्मल फोर्स लग रही है. That's it. Of course, आप ये नहीं करते, आप ज्यादातर ये कर लेते हो स्ट्रेट अवे होके, क्योंकि नॉर्मल फोर्स आपके लिए जितना मर्जी मैं बोल लूँ ना, आपकी नॉर्मल फोर्स हमेशा वेट के बराबर ही होती है. बट इन दिस केस इट इज, बट इफ आई डू इट इन एन एलिवेटर ऑफ कोर्स इट वोंट बी इक्वल, ओके, बट एनीवे, ओके. सो व्हाई कैन आई जंप फ्रॉम हियर टू हियर? कहाँ एक डब्बा, कहाँ एक पॉइंट पार्टिकल? व्हाई कैन आई डू दैट? इट्स देयर. बता दो. Why don't I consider the intermolecular forces within the box? Because those are internal forces. Effectively मैं बॉक्स के ऊपर ये वाली इक्वेशन लगा रहा होता हूँ. एक्सेप्ट कि आपको ए लेवल में सारे लोग कहते हैं ये बिल्कुल चूसने वाले बच्चे हैं, ये देख लेंगे तो डर के भाग जाएंगे. Effectively that's what you are doing. The total external force on the box are precisely these. बाकी सारे तो internal forces हैं. If I treat the box as my system of particles, all the intermolecular forces within the box are internal forces. The only external forces acting on the box, so ये तीन है. That's why you only need to consider these three. You don't need to worry about magnetic forces, you don't need to worry about any electrostatic forces and so on and so forth. You don't need to worry about कि भाई अच्छा मेरे हाथ जो हैं वो सिर्फ इधर फोर्स लगा रहे हैं भाई, बाकी डब्बे को तो टच ही नहीं कर रहे, तो फिर क्या है, कैसे मैं ये कंसीडर कर रहा हूँ कि भाई ये सारे डब्बे के ऊपर ये फोर्स लग रही है? वेल इसलिए कंसीडर कर बिकॉज आई एम ट्रीटिंग द होल बॉक्स एज माय सिस्टम ऑफ पार्टिकल्स. Any external force that is acting on the system of particles must be considered over here. In other words, this can be written as, for this case, F plus the weight plus the normal force equals the mass of the box times the double derivative of the center of mass. और ये डबल डेरिवेटिव हम निकालते हैं. ये डबल डेरिवेटिव को आप कह सकते हैं दिस इज काइंड ऑफ द एवरेज एक्सलेरेशन ऑफ द एटम्स और मॉलिक्यूल्स दैट कंप्राइज द बॉक्स. आपकी टोटल फोर्स से मास ऑफ बॉक्स इधर जाएगा, ये टोटल फोर्स बनेगी, इससे आप रिड्यूस करते हो ये. यू आर काइंड ऑफ लुकिंग एट हाउ डज द सेंटर ऑफ मास ऑफ द बॉक्स मूव. ओके, आप इसलिए वो जोक बना हुआ है सारे साइंसदान जो है वो काओ को स्फीयर बना देते हैं, ओके, स्फीरिकल काओ. ओके, द रब इज दैट वी गोस वन स्टेप बियॉन्ड दैट. एक दफा हमने सेंटर ऑफ मास का मोशन को इन्वेस्टिगेट कर लिया, वो अगला स्टेप आपको नहीं बताता क्योंकि द नेक्स्ट स्टेप इज टू एनालाइज द मोशन अराउंड द सेंटर ऑफ मास. So then if you analyze the motion around the center of mass, which we'll do when we come to rotations, joy, okay, a cow is very different from your friend that I've thrown off the rooftop. Okay, अगर मैं गाय को फेंकूं और आपके दोस्त को फेंकूं, of course they'll execute different motions. The center of mass will behave similarly, but the motion around the center of mass will be different. Okay, so that's the first use. अब आपको अगर सर इसका क्या फायदा, ये मिड टर्म में तो क्वेश्चन में नहीं आ सकता, वो तो पहले ही मैं कर रहा था. But you know, it's good for you to be able to sleep at night, okay, if you have a scientific conscience, okay. But anyway, okay, we do not. Okay, but anyway, okay. So the second use. अब एग्जाम वाले क्वेश्चन आ रहे हैं. The second use is that this is what leads to something extremely important, which is conservation of something. I mean conservation of energy हो गई है तो उसके बाद क्या होगा conserve क्या है? Conservation of linear momentum. Now in this course generally अगर मैं इस lecture में momentum कह रहा हूँ I mean something called the linear momentum. In A levels it didn't matter because in A levels the only momentum you ever saw was linear momentum. FSC वाले दो फॉर्मूले याद कर लेते हैं एंगुलर मोमेंटम के और फिर समझते हैं हमें एंगुलर मोमेंटम भी सीख लिया है. You know, I mean, if you are an ostrich who buries their head in the sand, that's fine, okay, but you know, you haven't really learned anything about angular momentum. But anyway, this equation is precisely what leads to the conservation of linear momentum, okay, and we'll build up towards that. Okay, so first of all, let me just show you very clearly कि linear conservation of linear momentum आता किधर से. Let's deal with a special case जहाँ external force, total external force is 0. Okay, so I'm not saying कि कोई forces लग नहीं रहे. That would be an incredibly boring situation. Right? So you know, two particles not exerting forces on each other would imply कि वो बहुत दूर हैं बस आपस में अपनी मौज मस्ती कर रहे हैं. Okay. Physics is always about interactions. That's what makes things interesting. Okay. So I'm not saying that the force is 0. I'm saying the total external force is 0. So for example, two billiard balls may be on a collision course. If I consider only one of these billiard balls as my system, the total external force on this is not 0 throughout. Yes, in this case generally it will be true that the weight will be equal to the normal force. But when the two billiard balls collide, this billiard ball does exert a force on this billiard ball. So there is an external force on this billiard ball because I'm treating the system as just only this billiard ball. However, and this will be a common trick that you will see over and over again. This is so powerful because you can always redefine your system such that your unknown force. In general, when I'm looking at colliding billiard balls, very often I don't know the forces that the billiard balls exert on each other. If I don't know any force, what's one way that I can get by without knowing that force? I can still make progress even if I don't know that force. उसको internal force बना दो ना essentially. This equation only looks at the external forces. ये आपकी ये वाली equation है. So if I redefine my system, if I say that both billiard balls, for example, are part of my system, then the forces that the two billiard balls exert on each other are internal forces. They'll never show up over here. So if I redefine the two billiard balls as my system, then the total external force is 0, provided you know there is no friction. And then I am back to this case. So basically just by enlarging your system, you can come about this situation. Just make any force that is at play, make it an internal force. Yeah, sure. But whether that's a useful exercise to do or not, that's a separate issue. कई दफ़ा आप इतना enlarge ना करो कि हर चीज़ internal force बन जाए, then it becomes very boring. Okay, फिर आप कुछ भी नहीं निकाल सकोगे. करेंगे ढेर सारे इसको applications करेंगे. Okay. So if this is true, then what can I write? Down? I can write down obviously because the total external force is 0 and the total external force equals the total mass times the double time derivative of the center of mass. And then you just tidy this up. बाकी तो बस आपने इसको थोड़ा बहुत मसाज करना है essentially है. So the first step that you do is that it's always much easier to visualize the first derivative compared to the second derivative. So what you do first is that you look at, say, let's define the first derivative as some separate quantity. dr by dt, I intuitively know that dr by dt should correspond to some kind of the velocity of the center of mass, the velocity corresponding to the center of mass. So that's just a definition. Okay. And in terms of this definition, I can then write this equation as dv by dt. And I can pull the derivative outside and I can get and now just to tidy things up further, so this is one definition, let me define another quantity. Capital P as capital M times capital V. So I've just made just two definitions of two quantities. One is the velocity corresponding to the center of mass, the other one is the what is called the linear momentum of my system. So capital P is referred to as your linear momentum of your system, and this then implies that what can I then say about dP by dt equals 0, and then what can I then say about capital P? Capital P is, so capital P is constant, as in it's conserved. Conserve का मतलब है कि वो quantity change नहीं होती. Of course, linear momentum in general is not conserved. आपको मैं उल्टा करके यूं करके फेंकूं, क्या होगा? आपका सर जाके टक्कर मारेगा जमीन के साथ. आपके सर का मोमेंटम कंजर्व हुआ है? ऑफ कोर्स नॉट. पहले आपका नॉन जीरो, टक्कर से जस्ट पहले नॉन जीरो था, नीचे की तरफ आपका सर जा रहा था, कुछ देर के बाद उधर यूं करके परे हुए होके. ऑफ कोर्स द मोमेंटम ऑफ योर हेड इज नॉट कंजर्व्ड. Why is it not conserved? It's because the total external force on your head was not zero. If you throw a tennis ball at a wall, okay, it bounces back. The linear momentum of the tennis ball is not conserved. Of course it's not. The wall exerts a force on the tennis ball. That's why it isn't. Whenever the linear momentum changes, there must have been a force. That's what this equation is telling you. Okay, right? That the force equals that that. Okay. अभी तो मैं special case deal कर रहा हूँ जहाँ ये external force 0 है, so that's why capital P is conserved. In general, it won't be. Okay. Okay, so capital P is conserved. A translation that it remains constant. Just like you have the conservation of energy. Energy is conserved, that means that the total energy remains constant. If the total external force equals 0. That's your law of conservation of linear momentum, which follows as you have seen from here. अब कहता सर जी रेड स्पॉट में तो कैपिटल P का हमेशा जिक्र नहीं होता था. रेड स्पॉट में तो you have two billiard balls, इसका मोमेंटम हम निकालते थे M1U1, M2U2, फिर कोलिजन के बाद हम कहते थे M1V1 और M2V2. ये कैपिटल M और कैपिटल V ये किधर से आ गए हैं? It's the same thing, except that I'm taking a shortcut. मैं आपको बल्कि थोड़े स्टेप्स में शो कर रहा हूँ. Okay, let's just go back to the definition of capital P. Capital P is equal to M times capital V. But what is capital V? Capital V is the time derivative of capital R, which is and this equals capital M to constant hai, and all the masses of the particles are also constant. The derivative will only see these position vectors. इनका time derivative क्या होगा? What's the time derivative of Ri? The velocity of the ith particle. So this is actually nothing other than MIVI over capital M. ये red spot की यादें ताज़ा हुई हैं शायद. For two particles M1V1 plus M2V2. Okay. So this implies that since this equals that, this clearly implies that capital M times capital V, in other words capital M को उस side पे ले जाओ, equals, and therefore this equals, you can consider the total linear momentum as the sum of MIVI, or you can consider it as the product of the total mass times the velocity of the center of mass. Both are guaranteed to give you the same answer. Okay? Right? And this also shows that if a single point particle hota, if your system was just a single point particle, uska linear momentum kya hota? MV. You just have the mass of the point particle times the velocity of the point particle. So each of these terms is actually what? each of these terms is actually the linear momentum of each point particle within your system of particles. So you can also write this as that. Right? And if the total external force is 0, that capital P is constant. I mean, rocket के case में the total external force won't be 0. And you'll see कि total rocket का momentum change होता है, hopefully, वरना बड़े फुस-फुस rocket है. Okay, the rocket remember has to fly upwards. उसने speed up करना है, अगर speed up करता है तो of course उसको momentum change होता है. Okay? Anyway. We'll come to that. Right now, I'm just dealing with a simple case जहाँ ये चीज़ 0 हो गई. Okay, so let's do some simple problems related to this. Watch closely, क्योंकि इन problem में थोड़ा सा दिमाग लगाना पड़ता है. In contrast with many other problems which you can just do blindly. You have some cannon. जिसे कोई firework shoot करते हो, okay? It's a firework cannon. You are standing on horizontal ground, and with some angle theta, you shoot a firework with some speed u. और मैं कहता हूँ इसकी range क्या होगी projectile की? In the absence of air resistance. और आपका तो उसी वक्त यूं काम के पेन नीचे गिर जाता है और मुंह में पानी भर जाता है. ये तो मैं कर सकता हूँ. बिस्मिल्लाह बिस्मिल्लाह. Okay, and of course, many of you will directly say u square sine 2 theta होगा, right? Okay, because I know that theta 90 degrees पे range 0 होनी चाहिए, so तो इसलिए आपका sin 2 theta हो सकता है, sin theta नहीं हो सकता. Anyway, so I have this. Okay, फिर आप values सर इसका center of mass से क्या ताल्लुक था? Of course कोई ताल्लुक नहीं था, hold on, okay. आपके let's modify the problem now. आपके फायरवर्क आपने फायर की है जब बिल्कुल टॉप पे गया, okay? जब बिल्कुल टॉप पे गया, and that's just to simplify the problem. जब बिल्कुल टॉप पे गया है, it explodes into 2 fragments. जिस तरह फायरवर्क को एक्सप्लोड करना चाहिए. It's a very useless firework कि एक्सप्लोड करके फ्रैगमेंट्स में नहीं डिवाइड होता. अदरवाइज तो बस आपने कुछ और ही छोड़ दिया, okay? Okay, so you have a firework that reaches the very top of its trajectory and explodes into 2 fragments. अभी भी काफी फुस-फुस firework है क्योंकि it only explodes into 2 fragments rather than many fragments. But anyway, okay. So you have this firework that goes up and explodes into 2 fragments, and what's given to you, just to make the problem concrete, is that one fragment goes backwards horizontally. And it goes backward horizontally such that it ends up back on you. You have the good sense to step out of the way, hopefully. Okay, so nothing bad happens. Question. There's a second fragment, of course. Question is essentially what happens with the second fragment. Does it go here? Does it go down? Does it go like that? How does it travel? Okay, so by and large, most of the class thinks कि वो horizontally travel करेगा. Next question. Where does it land? ये इधर लैंड करेगा, इधर लैंड करेगा, उधर लैंड करेगा. एंड नेक्स्ट क्वेश्चन, क्वांटिटेटिवली बताओ किधर लैंड करेगा, एग्जैक्ट लोकेशन बताओ. डोंट जस्ट टेल मी कि इस पॉइंट के लेफ्ट पे लैंड करेगा, उधर लैंड करके राइट पे लैंड करेगा. उल्टा हो गया मेरा. लेफ्ट पे लैंड करेगा, इधर लैंड करके राइट पे लैंड करेगा. टेल मी एग्जैक्टली किधर लैंड करेगा इन द एब्सेंस ऑफ एयर रेजिस्टेंस. यस, थैंक यू. कोई मोमेंटम से ताल्लुक है ऑफ कोर्स, ओके. So the first thing that you have to do is to again start किधर से करेंगे. Free body diagram, okay. So you fire the firework and the only force acting on the firework is the weight. Because of the weight, it's bending like that. It follows a parabolic trajectory. It reaches the top. Then it explodes into 2 fragments. अब मुझे एक फ्रैगमेंट का पता है कि पोजीशन किस तरह चेंज हो रही है, मुझे दूसरे फ्रैगमेंट को कुछ भी नहीं पता. Why does this second fragment follow some trajectory? उस पे क्या हुआ है दूसरे fragment पे? Well, during the explosion, this fragment exerted the force on the second fragment. But I don't know that force. Explosion हुआ है ना, the 2 fragments must have exerted some repulsive force on each other. A huge repulsive force on each other to actually separate themselves from one another. And I don't know the repulsive force. तो फिर मुझे क्या करना चाहिए? You define your system in such a way that that unknown force becomes an internal force. Define your whole firework as your system of particles. Then the two fragments are part of your system of particles. Okay, so that take it step by step. Okay. Okay, so it reaches the top, then it explodes into two fragments. Okay. The momentum just before the explosion, the linear momentum of my firework is horizontal. That was why I said कि भाई ये simplicity of the problem के लिए मैं कह रहा हूँ कि बिल्कुल top पे जाके explode करता है, because at the top उसका momentum सिर्फ horizontal है. So the linear momentum of the two fragments, total linear momentum of the two fragments just after the explosion क्या होगा? That will also be horizontal. आपको पता है कि just after the explosion ये वाली fragment is just moving horizontally. तो अगर total linear momentum आपको horizontal ही चाहिए और एक फ्रैगमेंट का लीनियर मोमेंटम हॉरिजॉन्टल है, तो दूसरे फ्रैगमेंट का क्या डायरेक्शन होगा लीनियर मोमेंटम का? दैट हैज टू बी हॉरिजॉन्टल. इफ दिस डिड हैव अ वर्टिकल कंपोनेंट, दैट वुड इमीडिएटली वायलेट द कंजर्वेशन ऑफ लीनियर मोमेंटम, क्योंकि जस्ट बिफोर द एक्सप्लोजन द लीनियर मोमेंटम ऑफ द फायरवर्क शुड बी इक्वल टू द लीनियर मोमेंटम ऑफ द फायरवर्क जस्ट आफ्टर द एक्सप्लोजन, बिकॉज ड्यूरिंग द एक्सप्लोजन कौन सी फोर्स लगी है? वेट. But the weight is acting vertically. That can only change the vertical momentum of the firework, not the horizontal momentum of the firework. So the horizontal momentum of the firework must be conserved. And the total horizontal momentum before the explosion is horizontal. The momentum after the explosion, one of the fragments is horizontal, so the second momentum must be horizontal. Otherwise, total linear momentum after the explosion का कोई vertical part भी आ जाएगा, which would violate the कंजर्वेशन ऑफ लीनियर मोमेंटम. तो ये तो हमें पता चल गया कि भाई दूसरी फ्रैगमेंट मस्ट इनिशियली मूव हॉरिजॉन्टली. अब अगला सवाल ये है कि ये आके ये ज्यादा दूर लैंड करेगा, इधर लैंड करेगा, इधर किधर लैंड करेगा? Okay, yeah, that's a good point. Okay, suppose that they split up into equal fragments. Original mass m है, इस फ्रैगमेंट का mass m/2 है, इस फ्रैगमेंट का mass m/2. Now what? Well, essentially the initial linear momentum points like that. आपका just after the explosion एक linear momentum इस तरह हो गया. The sum of the linear momentum after the explosion should equal the linear momentum before the explosion. तो ये दूसरी fragment का linear momentum क्या होगा? काफी ज्यादा होगा, because you want a total linear momentum to be pointing in that way. एक fragment का उस direction में हो गया है, तो दूसरे फ्रैगमेंट का काफी ज्यादा बड़ा होगा उस साइड पे, सो दैट यू गेट द सेम लीनियर मोमेंटम एज द इनिशियल लीनियर मोमेंटम. सो ये काफी तेजी से आगे जाएगा, विच यू कैन गेट स्ट्रेट अवे. ये एक्सप्लोजन क्यों हुआ? देयर वाज अ ह्यूज रिपल्सिव फोर्स बीइंग एक्साइटेड बाय द फ्रैगमेंट्स ऑन ईच अदर. ये काइंड ऑफ ऐसे है जैसे दो ब्लॉक स्प्रिंग से बंधे हुए थे और ऊपर जाके अचानक जो है रिपल्सिव झुज करके क्यों सेपरेट हो गया, तो ये वाला किधर जाएगा? जूम करके आगे जाएगा. सो इट शुड लैंड समवेयर ओवर हियर. I don't know. ये भी निकालते हैं. Okay. Next question. What's the time taken by fragment 1 to reach the ground? What's the time taken by fragment 2 to reach the ground? As in what I'm asking is, do they land on the ground simultaneously or do they land on the ground at different times? Why? क्योंकि initially उनके vertical velocity 0 है. And the acceleration that they experience vertically is the same. Like I said, ये ज़्यादातर लेक्चर में सारे अल्फाज ही अल्फाज हैं, कैलकुलेशंस बहुत कम है. सो दे बोथ एसेंशियली, अगर आप कोई हॉरिजॉन्टल लाइन ड्रॉ करो इधर, बोथ द फ्रैगमेंट्स विल बी लाइंग अलोंग दिस हॉरिजॉन्टल लाइन. किसी भी टाइम पे वो एक ही वर्टिकल लेवल पे आपको मिलेंगे, बिकॉज दे आर कवरिंग इक्वल वर्टिकल डिस्टेंसेज इन इक्वल टाइम्स. ओके, नाउ लेट्स लुक एट द सिचुएशन जस्ट बिफोर दे हिट द ग्राउंड. आपको एक फ्रैगमेंट इधर मिलेगी, एक फ्रैगमेंट जनाब आलिया आपको इधर मिलेगी. देयर सेंटर ऑफ मास इज समवेयर. इन दोनों फ्रैगमेंट्स का सेंटर ऑफ मास किधर होगा? लेकिन बीच किधर बनेगा इस केस में? बीच इधर बनेगा जनाब, ये इधर, जो आपकी ओरिजिनल ट्रेजेक्टरी के अलोंग बनेगा आपका सेंटर ऑफ मास इनका. क्यों? बिकॉज द एक्सप्लोजन ने क्या किया? एक्सप्लोजन के दौरान इंटरनल फोर्सेज लगी हैं. Can internal forces change the motion of the center of mass? No. That is built into that equation. The motion of the center of mass is only affected by external forces. जब explosion हुआ है, the only forces at play were internal forces. तो जो explosion के बाद fragment, sure, एक fragment उधर गई है, एक इधर गई है, but उन दोनों का जो combined center of mass है, that kept on following the original trajectory. क्योंकि center of mass originally तो follow ये y trajectory का आ रहा था. Internal forces लगी हैं तो अभी भी center of mass उनका यही trajectory follow का आ रहा है. The motion of the center of mass is unaffected by any internal forces. आपका एक्सप्लोजन हुआ उसमें इंटरनल फोर्सेस लगी हैं, ठीक है, एक्सटर्नल फोर्स लगी कोई नहीं है. तो अब एक्सटर्नल फोर्स कोई नहीं लगी एक्सप्लोजन की वजह से, तो सेंटर ऑफ मास का मोशन चेंज हुआ होगा. ये दो फ्रेगमेंट्स मूव कर रही हैं, उनका सेंटर ऑफ मास आई कैन फाइंड इट आउट एट एनी इंस्टेंट ऑफ टाइम. जैसे कुछ देर के बाद फॉर एग्जांपल आपकी ये वाली फ्रेगमेंट जो है, आपकी ये वाली फ्रेगमेंट इधर है, आपकी ब्लू फ्रेगमेंट इधर है. This is at the same time. In what I am claiming is कि उनका center of mass इधर है. Of course इस डायग्राम पे नहीं नजर आ रहा है क्योंकि काफी not to scale मैंने डायग्राम बना दिया है. But anyway, क्योंकि the combined motion of the two fragments must keep on following the original trajectory. Okay? क्योंकि external force कोई नहीं लगी explosion के दौरान. So as in only an external force can change the trajectory of the center of mass. That's what this equation is telling you. हाँ. हाँ. उसके बाद क्या है? हाँ. नहीं, एक मैं बता दिया कि एक पीछे जाता है. इट डिपेंड्स ऑन ऑफ कोर्स एक्सप्लोजन कैसे हुआ है. एक फ्रेगमेंट जो है पीछे गई है और दूसरी मस्ट आगे गई है. जरूर हो सकता है कोई और क्वेश्चन में दूं कि एक फ्रेगमेंट बिल्कुल नीचे चली गई है और दूसरी फ्रेगमेंट फिर किधर गई होगी. एंड आई मीन देयर आर मेनी वेरिएंट्स ऑफ दिस प्रॉब्लम. ओके, जरूरी नहीं है कि एक फ्रेगमेंट बिल्कुल पीछे ही जाए. हाँ. क्योंकि दोनों इस केस में फ्रेगमेंट्स इक्वल मास के हैं तो सेंटर ऑफ मास तो बिल्कुल दरमियान में होगा एट एनी गिवन टाइम. लेकिन आई आल्सो नो कि भाई हाँ या वो टू स्केल नहीं है इसलिए आपको लग रहा है. ओके, नाउ अब ये फिर गिवन दैट अब ये वाला पॉइंट मैं कैसे निकालूंगा? यू जस्ट सेट इट अप कि भाई आप कह दो कि भाई ये मेरे एक्सिस है, दिस इज एक्स एक्सिस, दिस इज वाई एक्सिस. द पोजीशन ऑफ द सेंटर ऑफ मास, लेट्स कॉल इट कैपिटल एक्स. जस्ट बिफोर द कोलिजन क्या है? Capital X just before the collision is m/2. This blue fragment का क्या position है? Thank you. And what about this second fragment? वही तो निकालनी है. उसको कोई unknown x रहने दो, small x. Divided by, इसको किसे divide करूंगा? The total mass of the two fragments which is m. और ये capital X है किसके बराबर? इफ आई से ये जो आपने R निकाला था ये आपका R था, तो कैपिटल X किसके बराबर है? इधर, which is equal to 2R. This equation is nothing other than the mathematical statement of the fact that the trajectory of the center of mass does not change due to the explosion. बाकी बस आप ये तो हलवा मैथमेटिक्स है. ये तो आप इस पूरे चैप्टर में ना कोई डिफरेंशिएशन है खास, ना कोई इंटीग्रेशन है. द इक्वेशंस आर रिडिकुलसली सिंपल. द ओनली प्रॉब्लम इज कि आपको वो इक्वेशन सेटअप नहीं करनी आएंगी. हाँ जी, या देन यू जस्ट मॉडिफाई द कैलकुलेशन. नहीं, सेंटर ऑफ मास विल स्टिल फॉलो द सेम ओरिजिनल ट्रैजेक्टरी. सेंटर ऑफ मास की ट्रैजेक्टरी तब भी नज हो सकती है अगर कोई एक्सटर्नल फोर्स लगी हो during the explosion. So then you just solve this and you get m/2 times x divided by m equals 2r. ये m और ये m कट गया, so x/2 is equal to 2r. d को मान गए हैं. And therefore x is equal to तो अगर ये r है, ये आपका 2r है और ये पूरा डिस्टेंस जो है दैट इज 4r. The second fragment lands a distance of 4r away. Okay? देखो मैथमेटिक्स कितनी थी? एक लाइन, 2 लाइन, 3 लाइन. एक्सेप्ट के आपके मार्क्स अगर मैं गिनूं तो 0 + 0 + 0 = 0 है. हाँ. तो फिर इधर कैलकुलेशन में इधर कोई चेंज नहीं आता, इधर आपका चेंज आता है, इधर और इधर. करो ना, प्ले अराउंड विद वेरिएंस ऑफ दिस प्रॉब्लम. ओके, आपको बेसिक आइडिया तो मैं दे दिया. ओके, हाँ. वो डिफरेंट होगा, ऑफ कोर्स यू विल गेट ए डिफरेंट आंसर फॉर स्मॉल एक्स. हाँ हाँ, एग्जैक्टली. अच्छा, लेट्स डू अनदर प्रॉब्लम. So you can see, yeah, essentially it was related to conservation of momentum, very closely related to conservation of momentum, but I never use, m1 u1 plus m2 u2 equals m1 v1 plus m2 v2. Okay, so you have to think slightly beyond that. Okay, it's not as in problem में आपको थोड़ा सा सोचना पड़ता है, कोई बंदरों की तरह m1 u1 plus m2 u2 नहीं लगाना होता. Okay, अच्छा जी, let's do another problem. The Romeo and Juliet problem, लेकिन ये हर कोई कहता है कि लोकल कॉन्टेक्स्ट दिया करो, तो चलो लैला मजनू प्रॉब्लम बना देते हैं उसको. कैसा नहीं है? Okay, आपको कैसे? This is the closest you'll get to humanities course in this course. Okay, so there's a guy, of course, Majnu. Over here there's a boat. बोट के लेफ्ट साइड पे मजनू जनाब खड़े हुए हैं या बैठे हुए हैं, नेवर माइंड. And then there's the beach, land, this is water, और इधर, of course इधर you can guess who. Okay, so इधर लैला खड़ी हुई है, उधर बोट में मजनू है. What happens in this problem, of course, is, get your mind off the gutter. What happens is, Majnu walks. That's the only thing he does, and then cut. Okay, Majnu walks from the left side of the boat to the right side. Okay, what happens after that? Take a humanities course. Okay. Anyway, so we're not really interested. Although I'll give you the prequel of what happens after that. Once Majnu reaches the right end, Majnu jumps off the boat. What happens and lands on the shore? Okay, so you have a boat of length L. Okay, and the first question, Majnu initially stationary. Okay, so bas aram se baitha hua hai. He's not excitedly jumping around. Maybe the case, but since this is physics, he's just stationary. And then he just walks to the right end. Once he reaches the right end, he stops. Consider karta hai ki, is Lala really worth it? Okay. He might not be able to complete the jump, so he will drown probably. Okay, so anyway. So he reaches the right end and stops. And the question is that, okay, he starts walking and then he comes to a stop at the right end. What happens to the boat? That's the question. आपको कोई सारा अस्तगफिरुल्लाह, इतने romantic scenario में आपने boat? Who cares about the boat? Okay, but anyway, since this is physics, okay, we do care about the boat. Okay. I mean, I suppose करो कि ये boat काफी light है. Of course we care about the boat. I mean, you don't want something like Titanic. Okay, ऐसा है. हो सकता है plank होता. Anyway, okay. So क्या होता है boat को? So before we'll actually be able to compute कि boat को क्या होता है exactly. We'll be able to quantify कि boat को क्या होता है. हम एक number बता सकेंगे कि क्या boat को क्या होता है exactly. So मजनू का mass m कह दो, boat का mass capital M कह दो. लैला का mass भी होगा of course, लेकिन never mind. Okay, that's not important over here. I mean, मजनू की choices उसकी choices हैं, not important. Okay, so anyway. Okay, so you have so मजनू साहब जो उधर जाते हैं, boat को क्या होगा? You are assuming that no drag force is being exerted by the water on the boat. Okay, so initially the weight of Majnu, the weight of the boat equals the buoyancy force being exerted by the water. Hopefully, otherwise Majnu, this story comes to a very premature end, okay? So anyway, so initially the vertical forces are 0. The total horizontal force is also 0 because the boat is not moving, okay? मजनू साहब इनिशियली स्टेशनरी है, अब वो चलना शुरू करते हैं. वेल, कैसे चलता है वो? डोंट टेल मी कि टांगों से चलता है, ओके? दैट्स रिडिकुलस रिस्पांस, ओके? इन टर्म्स ऑफ फोर्सेस वो कैसे चलता है? He applies a backward force on the boat and corresponding to the boat exerts a force on the right on him. So मजनू साहब जब आगे जा रहे हैं, बोट पे ऊपर एक लेफ्ट पे फोर्स लग रही है. So the boat as a whole starts moving to the left. जब मजनू साहब राइट पे जाके रुक जाते हैं, बोट क्या तब भी मूव कर रही है? वेल, क्यों नहीं मूव कर रही? कर रही है या नहीं मूव कर रही? I mean, if you look at, there's this force that Majnu is exerting on the boat. We don't know that force. So what do? We make it an internal force. Majnu plus the boat. This is not romantic, okay? So Majnu plus the boat is our system, okay? So, yeah. Okay. I don't question Majnu's choices, okay? Whatever, okay? So Majnu plus the boat is the system, okay? And then the force that Majnu exerts on the boat is an internal force. So the total momentum of Majnu plus the boat must be conserved in this case. Because water को drag force नहीं लगा, there's no external horizontal force on the boat plus Majnu system. Water को drag force लगा नहीं रहा. The weights are acting vertically, the buoyancy forces are acting vertically. So the total horizontal momentum of the system of Majnu plus the boat must be conserved. जब Majnu initially stationary है with respect to the boat, and the boat is stationary with respect to the ground. Remember, we're doing this in the ground frame because that's an inertial frame. Total linear momentum क्या है? Majnu plus boat का 0, of course. Majnu is not moving, the boat is not moving. So it must remain 0 throughout. It must remain 0 throughout Majnu's motion, because there is no total external horizontal force on this system of Majnu plus the boat. So the total horizontal momentum must be conserved. इसका मतलब है जब मजनू साहब इधर आके रुक जाते हैं, बोट को क्या होना चाहिए? The boat must also stop. Otherwise total linear momentum 0 कैसे है? अब बोट रुक क्यों जाती है in terms of forces? Well, मजनू साहब चल के जा रहे हैं, उसने अपने आप को रोकना भी तो है. He has to decelerate himself. जब वो decelerate करने की कोशिश करेगा, वो बोट को आगे की तरफ पुश करेगा such that the boat exerts a force to the left on him. जब बोट उस तरफ जा रही है, जब बोट के ऊपर आगे की तरफ फोर्स लगाएगा तो बोट को क्या होगा? रुक जाएगी. That's why the boat stops. अब लेकिन during these two actions, during this first action of beginning to walk and then coming to a stop, बोट ने लेफ्ट को मूव करती गई है. So when Majnu comes to a stop at the end of the day, बोट as a whole थोड़ी सी लेफ्ट को शिफ्ट हो गई है. क्वेश्चन, कितनी शिफ्ट हुई है? Okay, now we have to figure that out. Fun, eh? Okay, so how do we figure that out? Well, total momentum is system का 0 रहता है horizontally. We are really interested only in the horizontal part, okay? But एक और चीज भी 0 रहती है. The total linear momentum is not just constant, the total linear momentum is also 0. Yeah, see? So therefore, अब क्या लिख सकते हो? M dr by dt is not just conserved, it's not just constant. This, remember, is nothing other than the total linear momentum. Capital M times d times capital R. This is not just conserved, this is not just constant, this is actually 0 throughout. Which tells me what? Which tells me what about capital R? Capital R is also constant. Not only is capital V constant in this case, capital R is also constant. As in the position of the center of mass does not change. It's not just that the center of mass does not move. The center of mass does not change either, okay? Of course, if the center of mass doesn't move, it doesn't go anywhere. So I say, okay, इधर आप सेट करो कि भाई ये मेरा coordinate system है. This is my x-axis. I'm only interested in the x motion. So I say capital X जब मजनू साहब left end पे हैं, where is the center of mass? The center of mass then won't be at the middle of the boat. The center of mass will be shifted to the left of the middle of the boat. मजनू की वजह से. So this will be equal to m times 0, mass of Majnu times the position of Majnu, plus capital M, mass of boat times L over 2, the location of the center of mass of the boat divided by total mass. That's the location of the center of mass of Majnu plus the boat before Majnu starts moving. Once Majnu reaches the right end, that's another way of saying कि boat left को shift कर जाती है. मजनू अगर राइट को मूव कर गया और बोट नहीं मूव की, सेंटर ऑफ मास किधर होगा? टू द राइट ऑफ द सेंटर ऑफ द बोट. लेकिन सेंटर ऑफ मास तो मूव ही नहीं करना. व्हाट्स द वे आउट देन? कि बोट पूरी की पूरी लेफ्ट पे शिफ्ट हो जाए. ओके, सो यू हैव कि जब मजनू साहब इधर आ गए हैं, सेंटर ऑफ मास इधर होना है, लेकिन असल में इधर होना है, तो पूरा क्या होगा? पूरी द होल बोट शिफ्ट्स टू द लेफ्ट. That's exactly what we have to find out. So this is the, so let me just draw another diagram over here. मजनू साहब इधर हैं initially, और फिर कुछ देर के बाद यूं हो गई सिचुएशन. This distance is L. यही small L आपने निकालना है. Small L is the distance that the boat moves. Okay, और फिर मजनू साहब जो हैं वो इधर फेर रहे हैं. This is the old position of Majnu, this is the new position of Majnu साहब. Okay, so this is x old, x new फिर क्या है? मजनू साहब का अब x कोऑर्डिनेट क्या है? कैपिटल L है सिर्फ. Yeah, exactly. बोट एज अ होल भी तो स्मॉल l मूव की है, तो मजनू साहब का x कोऑर्डिनेट कैपिटल L माइनस स्मॉल l है. प्लस बोट के अब सेंटर किधर है? L by 2 minus small l. Boat as a whole has shifted small l distance to the left. So you have m L by 2 minus small l divided by small m plus capital M. एक लाइन, दो लाइन. Small l is the distance that the boat moves as a whole to the left. That's exactly what you have to find out. ये ओए हाय, ये लो जी, अब नजर आ रहा है. दिस इज स्मॉल l. Okay, and then all you have to do is नहीं, this must be equal to that. क्यों? क्योंकि सेंटर ऑफ मास की तो नहीं लोकेशन चेंज होनी. The old position of the center, the old center of mass must equal the new center of mass. Why? Because इधर शिफ्ट हो गए. ये चौक के कलर की वजह से नहीं समझ आया, या वैसे ही लैला मजनू में कोई इंटरेस्ट खत्म हो गया? दोनों हो गए. हो गया. सब्र करो बे. मुझे पहले ये खत्म कर दे तो then we can come to the individual parts. Okay, so what you do is say that this must be equal to that. Why? Because the center of mass does not change, and then you get something very simple. M times L by 2. ये denominator तो दोनों के same है. If these two things are the same, the numerators must be the same. So M times L by 2 must be equal to small m times L times small l plus capital M times L by 2 minus L. And this equals ml minus m small l plus capital M times L by 2 minus capital M times L. And then you say, okay, then you just simplify this. ये इसके साथ कट जाता है, और फिर आपका आ जाता है that 0 equals ml minus m plus m times small l. And therefore, you get the grand result that small l equals m over that's what you have. Okay, again ये algebra पे ना focus करो. Essentially the important thing again is कि center of mass सिर्फ एक ही चीज change कर सकती है. The center of mass, the location of the center of mass can only be changed by external forces. You have defined your system as Majnu plus the boat. The center of mass of this system cannot change as Majnu walks because Majnu जो बोट पे फोर्स एक्सर्ट कर रहा है वो इंटरनल फोर्स है. बोट जो मजनू पे फोर्स एक्सर्ट कर रहा है वो इंटरनल फोर्स है. सो द सेंटर ऑफ मास डज नॉट चेंज. मजनू जब लेफ्ट से राइट पे आया है, द बोट एज अ होल शिफ्ट टू द लेफ्ट such that the center of mass does not change. And you can use this fact to calculate कि big small l क्या होगा. किधर है? हाँ, अगर टोटल एक्सटर्नल फोर्स कोई होती तो फिर चेंज होता. इस केस में नहीं है. नहीं, आप कोई बॉल फेंको, बॉल का सेंटर ऑफ मास चेंज हो रहा है. ऑफ कोर्स हो रहा है. बॉल का सेंटर ऑफ मास वो देखो पैराबोला में फ्लाई करता हुआ जा रहा है. क्या हो गया है? आई मीन यू थ्रो ए बॉल, पहले यहां है, कुछ देर के बाद यहां है. ऑफ कोर्स इसका सेंटर ऑफ मास चेंज क्यों चेंज हुआ है? बिकॉज ऑफ एन एक्सटर्नल फोर्स ऑन इट. जो कि क्या है इस केस में? वेट. इन दिस केस वेट है उनका, but there's a buoyancy force as well. So the net external force is 0 in this case. Okay?